So good morning to everyone. Let us begin the session. In today's session, we are going to continue the topic that we were in discussion, that is closure property. Let me just quickly open it. Okay. Uh, so in the previous session, we already seen how to find out the reflexive closure. As well as we have also seen how to find out the symmetric closure. If the relation is not symmetric, then how to get the closure. So similarly, in today's session, we are going to see how to find out the transitive closure. So closure of a relation property is what? It is when a property does not hold for a relation. How will we minimally augment the relation so that the property will satisfy that particular property. So reflexive closure, we already seen how to make a relation reflexive. So given relation R union with this delta, what is this delta? Delta is nothing but collection of all A comma A, where A belongs to set A. So this is your reflexive closure. Similarly, symmetric closure is what? Given relation R, and if the relation R is not symmetric, then how to make the relation symmetric? R union uh, yeah. So how to make the relation symmetric? For that, there is one more concept we should understand: inverse of a given relation R. So what is inverse of given relation R? If you are having relation R having all the ordered pair elements A comma B, then R inverse will have all the elements belonging to R inverse will be B comma A. You are just interchanging domain and codomain. Okay. So, for example, if you are having a relation R, let me just wait. Let us say your relation R is containing elements something like this: 1 comma 2, 2 comma 3, 6 comma 1, 8 comma 9, and something like that. Okay. Then let us say 5 comma 5. Okay. So can anybody tell me now what will be inverse of R? What will be the cardinality of inverse of R? Can anybody unmute and discuss? Let us discuss. What is cardinality of R? At least answer this question. What is cardinality of R? Am I audible? Please, someone please respond. At least respond. Am I audible?
Yes, sir.
Yeah. Thank you. So, what is the cardinality of R at present in this scenario? Yeah, someone quickly respond. What is cardinality of R here?
5.
5. Okay. If I want inverse of R, what will be the cardinality? Okay. What will be the inverse of R? Inverse of R, just now we have seen. Inverse of R is collection of all the elements of B comma A such that where A comma B belongs to R. So what will be R inverse here? Can anybody tell me now? What will be R inverse? What will be the elements of R inverse here? What should I write? For all elements A comma P belongs to R, B comma A is the element which is belonging to inverse of R. That is called R inverse. So what should I write?
So 2 comma 1,
Correct. Very good. Next.
3 comma 2,
Continue. Very good. Next.
1 comma 6,
Correct.
9 comma 8,
Correct.
and 5 comma 5.
Very good. So the cardinality of inverse of R is also remaining as it is. It is also same as what is your cardinality of R. Now, what is the point of discussion that we are discussing right now? We want to find out the symmetric closure of R. If the given relation R is symmetric, then there is no need of finding out symmetric closure. If the given relation R is not symmetric, then how we can forcefully make that relation R symmetric? So it's simple operation. Here you need to have just R union, R inverse, inverse of R. It is definitely your, uh, I'm not able to draw the symbols here, so therefore I'm typing here symmetric closure of R, that is equal to. So that is equal to what? R union inverse of R. If you do the union of these two, if you do R union inverse of R, you will get a relation which is symmetric closure. Is it clear or not? Please respond in the chat box. Any questions related to this symmetric closure? Please quickly give the feedback in the chat box whether it is clear or not. Yes or no? If any questions, please don't hesitate to ask me. I will attempt to it if it is required. Okay, all right. Majority are yes. Let's proceed ahead. So the point of discussion, symmetric closure of R is R union R inverse. That's it. Let's go ahead. Transitive closure. Now, what is transitive closure? Closure is nothing but forcefully we are making relation to some transform R dash, which is satisfying that particular property. That's we call it as a which kind of property? If it is reflexive property, then reflexive closure. If it is symmetric property, symmetric closure. If it is transitive, then transitive closure, and something like that. So now everyone kindly go through this relation R. Can you tell me, is it satisfying transitivity? Yes or no? Is this relation transitive? Yes or no? Yeah, kindly give quick feedback in the chat box. Is this relation R is transitive? Yes or no? Okay. Viraj is saying no. Palak is also saying no. Palak. Okay. So, Palak Kumari, can you unmute yourself and can you tell me if it is not transitive, then what is the counter example for this? Give me one counter example. Palak Kumari, unmute yourself and tell me.
Sir, your screen is not visible.
Okay, great. Just a moment. I lost connection with laptop. Just a moment. Kindly wait. I'm still trying my laptop to get connected. Is my screen visible now? Hello. Am I audible?
Yes, sir.
Yeah. So, Palak Kumari, can you please tell me why this relation R is not transitive? Use one counter
Yes.
example.
So it is not
Yes.
transitive because 1 comma 3 belongs to R,
Hmm.
3 comma 2 also belongs to R, but 1 comma 2 doesn't belong to R.
Hmm. Correct.
So it is
Absolutely
not
right. Perfect. Very good. So, we want to make this relation R forcefully transitive. So how to make it? Terms. Just now Palak has identified 1 comma 3, 3 comma 2, 1 comma 2 is missing. What other apart from this? If you take 3 comma 2, 2 comma 1, 2 comma 1 is also missing. If you take 2 comma 1, 1 comma 4, 2 comma 4 is also missing, and there are many more terms. So if we add those all missing terms into this relation R, then this relation R will become transitive. And this transformed version of this relation R is called as transitive closure of R. Okay. So how to make relation R transitive closure is little bit having more than one step activity. And let us try to understand how to minimally augment R, that is adding the minimum number of ordered pairs to have a transitive relation. So for that, Uh, okay, let us try to understand a concept called as path. We already seen what is diagram. A relation R can be shown in terms of graph, where nodes are represented as nodes or vertices are represented as elements belonging to that set, and a edge connecting one node to another node is nothing but it's a path, or I can say there is a association from A to B. So what is path in directed graph? A path from A to C in a directed graph G is a sequence of one or more adjacent R. So I will just directly show, for example, what is the way I am able to reach from A to B? So for that you need to hop from A to X1, X1 to X2, X2 to X3, Xn minus 1 to 2. If you are hopping from node A with these intermediate nodes and you are reaching to B, what is the length of this hopping? So what are the vertices intermediate A to X1, X1 to X2, X2 to X3, dot dot dot, Xn minus 1 and then Xn minus 1 to B. So it is having length M. If A and B, A is equal to B means what? If you are routing A to X1, X1 to X2, X2 to X3, dot dot dot, Xn minus 1 and again from to A means your source and destination is same, and you are having such path, then this is called as circuit, or it is also called as a cycle. Since the path returns to its starting position. So more details we will study when we start the graph, maybe after the IET one. The same concept is also you are learning in parallel subject, that is data structure. So what is the point that we are discussing at present? Let us say these are your vertices, these are the elements belonging to a set, and there is a relation R that is applied on the set to set itself, where you can see there is a relation from 3 to 1, 1 to 3, 3 to 2, 1 to 4. Okay. Now, there exists a path of length 2 from 1 to 2. If I want to move from 1 to 2, you can go from 1 to 3. This is length 1. And then from 3 to 2, this is another length 1. Add it. So there are two edges. You reach to node 2 from node 1. So in short, what I'm saying now, I am able, there is an association from node 1 to node 2 via length 2, means via some one intermediate vertex 1 to 3 and 3 to 2. So length 2, or alternative I can say vertex 2 is at distance of length 2 from vertex 1, means 1 to 3 and 3 to 2. Okay. Similarly, there exists a path of length 3 from 3 to 4. I want to move from 3 to 4. So 3 to 2, 2 to 1, 1 to 4. So 1, 2, 3. So the node 4 is at distance 3 from node 3. So there are no paths from 4 to 1. So it is at distance 0. No, distance 0 means what? It is not distance 0 exactly. 1 is at what distance from itself? It is at distance 0. It is source and destination. The node is itself connected with itself. So 0 length. 1 is connected with 1. 2 is connected with 2. If it is connected, then you will have a arc here. Let me use the yeah. If one is connected with itself, then you may have one more arrow here. At present, one is not connected with at present. But if you do have this self, this is called as self loop. Connected with itself, having zero length. So what is the length of 0? What is the length of 1 to 3? It is 1. What is the length of 1 to 2? 1 plus 1, that is 2. Something like that. And there are no path from 4 to 1. At present, there is no path from 2 to 2. Is it? No. There is a path. So you can go from 2 to 1. You can go from 1 to 3. And again, you can go from 3 to 2. So 2 is connected with itself by 3 links. Okay? Is it clear? Yes or no? Please let me know in the chat box. This concept called as path length. Yes or no? Please respond quickly in the chat box. If any questions, please let me know. Kindly quickly respond in the chat box whether this concept is clear or not. If it is clear, mention yes. If it is not clear, mention no. I'm waiting for the response in the chat box. I'm not getting any answers. So why it is so? Yeah, Palak Kumari, can you unmute?
Yes, sir.
Is it clear or not?
Yes, sir. It's clear.
Then please respond in the chat box. No? Then I'm asking the same thing. Everyone kindly respond in the chat box if the concept is clear or not. Accordingly, I will take a call whether to again reiterate or proceed ahead. Still, there are no response from the rest of the students. Chanvi, Sumit, Hussein, Arya, Shaukat Ali, Viraj, Rohini, Chetan, Karina, Shakti, Sumit. Okay. Whenever I am asking a quick feedback, please do immediately respond in the chat box so that accordingly I will have a plan for further education. So, having understood this, let's proceed ahead. So there is a path. What is path in relation? There is a path from A to B in R if there is a sequence of elements x1, x2, xn minus 1 with a1, a comma x1 belongs to R, x1 comma x2 belongs to R, xn minus 1 comma b belongs to R. Example, if this is your relation R having elements 1 comma 3, 1 comma 4, 3 comma 1, 3 comma 2, there exists a path in this R of length 2 from 1 to 2. How? 1 to 3 and 3 to 2. So therefore 1 to 2. Okay. We are able to relate 1 to 2 via intermediate vertex 3 for which 1 to 1 comma 3 is also in R, 3 comma 2 is also in R. Therefore 1 comma 2. You are able to relate. So you can say there is a path in R of length 2. Similarly, there is a path in R is having length 3 from element 3 to 4. How? You can see 3 comma 2, 2 comma 1. So you can establish 3 comma 1. And because of 3 comma 1 and 1 comma 4, you can establish 3 comma 4. So 3 to 2, 2 to 1, 1 to 4. So therefore 3 to 4 is not having length 3. There is no path in R from 4 to 1. Even 4 to 1, you can check out there is no element at domain position. This is domain position, this is codomain position. No single element at domain position having value 4. So therefore, you are not able to identify any elements which is relating from 4 to 1. Similarly, 4 to 2, 4 to 3, we are not able to find. So let R be a relation on set A. There exists a part in R of length n from A to B if and only if the symbol is pronounced as if and only if A comma B belongs to R raised to n. Now what is R raised to n? We already seen the composition of it. So we'll straight away proceed ahead. Then we will come back to this book and we'll straight away. Yeah, this is what we need to find out. R closure, R transitive closure. The star is equal to, which is a transitive closure. How we will find out this? It is basically union of R united with R composition R, that is R square, united with R composition R, that is R cube, united with dot dot dot, united with R raised to n. Now what is n? Let A be a set with n elements. So how long you can have this composition at the max? R raised to n. If you do R raised to n plus 1 time also, it will remain same. There will not be any further changes. Maximum composition we can carry out the level of composition, that is R raised to n. The point of discussion is what? We are able to find out this transitive closure, how you are uniting R with R square with R cube with R raised to n. If you do this, definitely the relation is transitive. So let us represent the given relation in terms of matrix form. To understand this, let us try to understand now how we find out this transitive closure. With one example, let us say this is relation R on set A containing elements 1, 2, 3. And what is the relation here? It is this is 1, this is 2, this is 3, 1, 2, 3. So what is the relation here? 1, 1, 1, 3, 2, 2, 3, 1, 3, 2. This is given relation R. Now, this is not transitive. Why? Because 3, 1 belongs to R, 1, 3 belongs to R, but 3, 3 do not belong to R. Therefore, this is not transitive. How to make it transitive? So what we do? We will find out the, okay, how many elements are here? First of all, there are 3 elements. So what is the cardinality of set A in this is 3. So how long you can carry out the composition? You can have R, you can have R composition R, that is called as R square. You can have R composition R, that is called as R raised to 3. Okay, the same thing is written in terms of matrix form, nothing else. So you need to find out now R composition R. How you find out R composition R? It is simple matrix multiplication operation. R composition R, you get this result. Same matrix is repeated here. So basically it is just a matrix multiplication. So you get R2. Now you want R3. How you will get R3? It is basically R composition R2. So you will get R3. And that's it. You what is the length of set A contains 3 elements, so maximum possible composition that you can carry out is up to n level.
So can you explain this again?
Yeah. So how to find out the R composition is I want transitive closure. So how you will union operation. This is your MR, sorry, this is your R square, and this is your R cube. You just have union operation. It is just like a OR operation. You will get the resultant transitive closure. So there is one algorithm for computing this transitive closure. Basically, this is called as Warsaw's algorithm. So what we do in this procedure for computing this transitive closure, we need to start with the original relation R, and this is your A, and we just copy this to some other intermediate matrix. And what we do for I equal to 2, n, do the following, that is A composition MR, you will get the Boolean matrix R square, and then B or A, this is join operation, that is union operation. So you will get again B, and this you need to repeat. This you need to repeat till n. So for example, this is your given original relation R that we are copying in A as well as B. So initially, what we are doing, we are just computing now whatever B that we are having, union A, the resultant B that we are getting, okay, that will be taken as it is for your MR3. This is your result. I'm just keeping this because straight away we are going to learn this algorithm. Yeah. So Warsaw algorithm, what we do iteratively, we construct 0 on 1 matrices to start with the original relation as W0, and in the next iteration for computing W1, this is a matrix, Warsaw matrix, where what exactly you are doing? You are just identifying all those association I to J such that there exists a path from Vi to Vj with interior vertices in V1. With interior vertices in V1 means what? What are those vertices which are connected to V1? And what are those vertices Vj which are connected from V1? So Vi comma V1 and V1 comma Vj. We are just all such pairs which are having interior vertices V1. Similarly, interior vertices V2. Similarly, V3 and something like that. You'll see this and then the things will get clear. Which is your original relation R. So what we do, we just transform this into W1, W0, you can call this as a W0. So W0 equal to MR. Okay. Now, how to find out W1? So it is simple. Basically, this is 1, 2, 3. 1, 2, 3. Okay. So at this stage, what we are doing, we are taking the first element. So we need to find out what is that something comma 1. We are identifying that. And what is that 1 comma something. So what is something comma 1? What are those elements which are related to 1? So it is 1. It is 3. What is 1 comma something? 1 is related to 1. 1 is related to 3. So what exactly we are doing now? We are having all possible combinations. Okay, 1 comma 1. If it is not marked 1, then you will mark it 1. 1 comma 3 is already marked. 3 comma 1 is already marked. 3 comma 3 is already marked. So there is no change at this point of time. There is no change. Similarly, we need to find out Now, what is something comma 2? And what is 2 comma something? So what is something comma 2? Who are related to 2? It is 2 and 3. Okay, who is related to whom? Who is related to only 2? Okay, 2 comma 2 is already present. Yes. 3 comma 2 is present. Yes. So no more change. Next is what is something comma 3 and 3 comma something. So who are related to 3? Only one element is related, that is 1. 3 is related to whom? 3 is related to 1 and 3. Okay, 1 comma 1 is already there. Yes. 1 comma 2 is there. No. 1 comma 2 is not there at all. And therefore, we need to mark that. So likewise, we need to find out. I'll just quickly go to the algorithm and then again we will revisit this. So procedure for computing transitive closure, we need to start with the original relation R, assign it to W, and now for k equal to 1 to n, if there are n elements in your set A, for k equal to 1 to n, do the following. For j equal to 1 to n, do the following. In every iteration, we are doing this. So for k equal to 1 to n means for all elements we are doing. Inside that, for I equal to 1 to n, and for j equal to 3, it is 3 times nested for loop. So the complexity of this algorithm is what? N cube, order of n cube. What exactly we are doing in this? We are trying to identify I comma j pair, wij, that is equal to original wij or wik and wkj. Whatever is the result, we are just doing OR and we will update this wij. So kindly take a snap of this in front of you. We will work out this with one example, then the things will be clear. So that is add this step K, add row K to all other rows which have 1 as intersection with the fifth column. So coming to this example, this is your matrix. We have assigned to W0, and now what we are doing? For K equal to 1 to 1, we follow. So what exactly we are doing for I equal to 1 to n and for j equal to 1 to n means we are talking right now 1 comma 1. Then we are computing now 1 comma 1, then 1 comma 2, 1 comma 3, dot 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 1 comma n. Once we finish this, then we will go for the second row. W2 comma 1, 2 comma 2, 2 comma 3, dot 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 2 comma n. And likewise, we will go to the last row, wn comma 1, n comma 2, n comma 3, dot 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 n comma n. We'll just, this is the way just to update this entry. This is what exactly we are doing. So coming here, initially W0 is this, now we need to find out W1. So how to find out W1 with respect to this algorithm? We are starting with so I'm just going back. Okay. So see here, what exactly we are doing? We just need to do this. So wij at present, I value is 1 and j value is 1. So we are talking about W11, that is this thing. We are talking about W11. So what is W11? This is basically wij that is equal to original wij, or you are taking some k. Now what is k? That k is equal to 1 to n. So you are taking one intermediate vertex, that is k, that is 1 to n every time. And that vertex will remain constant in this iteration. If you are starting with k equal to 1, so for all the entire matrix that we are computing, this element k will be intermediate element. Wik and k comma j. What is wik and what is wkj? So basically, please try to understand in a nutshell. All these wij is equal to, either it is equal to 1 or it is equal to 0. When it is equal to 1, when you have association from I to j, then you say wij is 1. When you do not have 1 is not related to, sorry, I is not related to j, then weight of the association is 0. W is nothing but weight, you can say. Weight of I comma j is 1 if they are connected. Weight of I comma j is 0 if they are not connected. Same thing applies here, I comma k and k comma j. So basically we are just dealing with 0 and 1 values. Okay. So coming to this wij, that is, so okay. So at present, let's try to understand here. We do have elements what 1, 2, and 3. So now we are starting with k value is this. This is your k at present. Okay. So what exactly we are trying to identify? We want to identify what is wij. So what is wij? Wij is your original wij. So what is the original value here? That I will write as it is. Let me just use another color. It is 1, 0, 1. These are all original values. 0, 1, 0, 1, 1, 0. Okay. And updation formula is what? Your original wij, or this is Boolean operation, or wik and wkj. Wik and wkj. Okay. So wij, what is I and j? I is nothing but row number, j is nothing but column number. So at present I value is 1 and j value is 1. So what exactly we are talking? W11. So what is, and what is k value here? That is 1. See, k is nothing but 1 to n. It is ranging from 1 to n. Okay. 1 to n. So we have taken element k. What exactly we are talking about present is wi comma I, that is w1 comma 1 is this original value, and I comma k. If I take now 1, there are 3 elements of 1. So w1 comma 1. So I will just write in terms of this current notation. This is 1 1. That is equal to w original 1 1 or w k value is also 1, that is 1 1, and w 1 1. So what is the result? Original w11 is 1, or this is also 1 and 1, So 1 and 1 is 1, 1 or 1 is 1 or 1 is 1. So this will remain as it is, no change. Similarly, if you go for W21, see your 1 2 not 2 1, you are just updating your you are just now taking the next column, that is W12, that is equal to W. So what I will do quickly, I will just update here itself. So I should write. So it is W12, that is your previous W12. Previous W12 is 0, and now you will have 1 comma 1, and see k value is 1 at present here. K value is 1, that is first element that you are taking. So it is I comma k and k comma j. So 1 comma 1, I comma k, 1 comma 1, and k comma j. K value is 1. So k comma, that is 2, k value is 1, 1 comma 2. So this will become 1 comma 2. So we are talking about now W12, that means this we need to update. How it is going to be updated? Basis on W11 and W12. W11 and W12. So what is 1 and 0? It is 0. 0 or 0 is 0. So it will remain as it is. Similarly, you go for W13. It will now be W13, and this will become 1 comma 1, and this will become 3 comma, sorry, 1 comma 3. K comma j. K is 1 and j is 3. So we are talking about now W13. W13 is this. Original is 1, or W11 is 1, and W13 is at present 1. 1 and 1 is 1, 1 or 1 is 1, so it will remain as it is. Likewise, now you have finished all columns. So, as per the algorithm, you have finished, you have finished j equal to 1 to n for I equal to 1. So, one iteration is over for all the columns for I equal to 1. Now, you will again repeat for I equal to 2. I equal to 2 means second row and all columns. Likewise, you will repeat for all the rows and all the columns for k equal to 1. Once you finish this, then you will increment your k equal to 2 and you will redo this step again. This is what we are doing in this. So once you complete this entire updation, this nested tree for loops, you will get the updated W matrix that will become W1. So at the end, when you complete this, your W1 is this, where this value is going to be updated. Okay. Now we will go for W2. It will remain as it is. And then you are just updating your k value to 3. And again, you are computing W3. So it will remain. There is a change like at this position. So this is what virtual algorithm is going to be executed. So what I suggest, we'll take one exercise for your homework. You try to complete that. I will post one exercise. Wait for a moment. The question is this. I'm just posing a question in the Excel. Use Warshaw's algorithm to find out the transitive closure of the following relation on set A that is equal to 1, 2, 3, 4. And there is some relation R from set A to set A itself. So there is one relation R1 that is equal to, let us say 1, 2, 2, 1, 2, 3, 3, 4, and 4, 1. Take another relation R2 for your exercise. 1, 2, 2, 1, 2, 3, and 3, 4. Take another relation R2 that is equal to 1, 4, 2, 3, 2, 4, 3, 4. Okay. So what is the exercise to you that you need to do? This is given relation R. You need to find out transitive closure of R. This is R. And this is your set A. So just now we have discussed the algorithm. Please first of all take the snap of this question. Find out the answer R1, R2, R3 iteratively. So you just execute this algorithm and find out the final W matrix for this three separate questions. This is the algorithm. Take a snap of this, and we'll discuss tomorrow in continuation with this topic itself. We'll stop at this point of time. You can post now your attendance in the chat box.